Good afternoon. My name's Tim Grove. I'm VGP President, and on behalf of myself and Fred Fry, who's President-elect, we'd like to welcome you to this year's VGP Daily Lecture. The Daily Lecture is part of what AGU calls the Bowie Lecture Series, which was developed in 1989 to honor past recipients of AGU's Bowie Medal. Our recipient is Reginald Daly, who got it in 1946, I believe. And also today, due to the precise and wonderful scheduling of our program committee, we have another Bowie lecture at 5 o'clock, the Tectonophysics Bowie lecture, which is the Birch lecture, which will be given by Paul Tapinier downstairs. I hope you all have a chance to attend that. And also, I want to remind you that tonight at 5:30 or so, we have the VGP reception jointly with Planetary, which is on the 3rd floor right here in this building. So everybody come and mix with our Planetary colleagues. So a little bit about Reginald Daly. He was quite an individual. He spent the first half of his career as a primarily field-based igneous petrologist, and the last half of his career worrying about the physical properties of the Earth's deep interior. And in that respect, I think it's fitting that we have today's lecturer, Bruce Watson, who spent a lot of his time worrying about the properties of fluids as they transport themselves through the Earth's solid. And I think that's what you're going to talk about today, isn't it, Bruce? Let's see. Yeah. Yeah, fluids and melts in the crust and upper mantle, new aspects bearing on mass transport. Bruce? I think you can just go over there and use your... Sure.
Well, thank you, Tim. My title has changed a little bit, but not the substance of my talk. I just had a few more weeks to think about how to phrase what I want to say. So this is my title, Mass Transport in Fluid-Bearing and Slightly Melted Rocks, Recent Developments and Future Directions. I have here a very brief outline of where I'm going to go with this talk today. I'm going to start assuming, and I will assume this throughout my presentation, that I'm speaking to a very general audience. So in fact, I'm deliberately going to avoid a lot of experimental details and just paint a sort of broad brush picture. But to help that along, I thought I would start with sort of a brief overview of the work that we're doing and try to put that in a historical perspective. I'll then move on and take 3 areas of research that we're currently engaged in where we have some tangible results, and I'll talk about those in sequence. And then I'll move on to talk about work in progress. I should apologize to those other people besides my group who work in this field beforehand, but I made a decision that I was going to talk mostly about our own work, not try to summarize the whole field, feeling really that there was no way I could be completely comprehensive, and therefore I should just focus on our own work rather than leave people out selectively. I owe thanks to certainly to our sponsors of this work, NSF and DOE Basic Energy Sciences, who supported this work over the years. My present collaborators I want to mention as well. David Wark, who's here today, is my co-worker on 2 of the 3 projects that I'm going to describe. I should say that his role in this has been really important too, because what I did was stick my neck out with funding agencies and say, we're going to do this work. And what Dave did was put his nose to the grindstone and call on his resourcefulness to figure out how to actually do it. Also, I should mention, I'm going to talk very briefly about the results of Mitch Nakamura's experiments on fluid infiltration. Mitch had a poster this afternoon at the Melt Migration Symposium. And my present postdocs, John Price and Glenn Gaetani, are also working on this project. One last reason that I chose the subject that I'm speaking about today is that I think it fits in pretty nicely with the symposium on melt migration, which ran this afternoon, I think, with a poster session, and will continue tomorrow afternoon with some oral presentations. Now, to begin with a sort of an odd historical perspective, I think this will set the stage for what I want to say. And I'm asking you really to think back maybe 20 years or so to the way in which researchers thought about fluids and melts at that time, at least most researchers. And I've given a couple of examples. One is in phase diagrams and the other in simple equations. But just to point out that something like a phase diagram certainly tells us a great deal about fluids and melts in the Earth. It tells us about the range of conditions over which they exist, tells us about their compositions, and even their proportions relative to solid if we know the bulk composition of the system. So those were and certainly continue to be an extremely important part of the way we think about fluids and melts today. Now, along with that, if you were, I actually was trained sort of as a trace element geochemist, and we spent a lot of time working with partitioning equations where fluids or melts would appear as this F in a partitioning equation for, this is, some of you will recognize as the batch melting equation for trace element behavior. But what I'd like to point out today is that neither of these says anything about the physical arrangement of the system. In fact, our system could consist of layers of solid, fluid, and vapor, for example. And as long as there's some mechanism for equilibrium, we can treat it in terms of the phase diagram or talk about it in terms of the phase diagram. And the same is true for these simple equations. Well, that then provides only a piece of the subject when it comes to talking about mass transport, which is my subject today. I want to talk a little bit about how fluids move through the Earth, how atoms and molecules move through fluids in the Earth. And when you come to look at it in those terms, you really need to go a little bit further than just thinking solely in terms of phase diagrams and equations. So, about 20 years ago, a new way of looking at least melts came into existence. And this really owes its origins or owes the introduction into the geologic community of the principles involved to Harvey Waff, who's now at the University of Oregon. Harvey Waff was thinking about the electrical conductivity of the mantle, and it was therefore crucial to him, to his understanding of conduction of the mantle, what is the physical distribution of melt in the system. And he published a photograph like this, not quite as detailed. It's actually quite fitting. This image is courtesy of Uli Fall, who was a student of Harvey Waff about 8 or 10 years ago. But what you see here is the physical arrangement of either olivine grains in the dark gray, and the light patches are basaltic melt, quenched basaltic melt. And studying this will tell you that there are grain boundaries in the system that are devoid of melt, and you can pick these out in many different places, one running through here. There are also things that look like little triangles, and these are numerous. Those are triple junctions that are wet with melt. In other words, the melt has penetrated along those junctions. And then a third aspect that you see is there are some larger pools of melt sitting amongst mostly smaller grains in this system. So this provides us with a way of beginning to think about transport in this system, and it adds another dimension, if you will, to the way we discuss fluids and melts. And I should say it's very important to note that while Harvey Waff introduced these principles in connection with melts in the mantle, the same exact principles govern microstructure development in rocks containing fluids, COH fluids, carbonate melts, and also metal oxysulfide melts. The same principles are involved. Okay. usually describe these principles in terms of this sort of catch-all word, equilibrium microstructure, which you see right here. And this is not an easy thing to describe, but it really refers simply to the physical arrangement of crystals and melt or fluid as determined by the interfacial energetics of the system. And here to illustrate this, I've shown a system of, looks like sort of randomly stacked cubes. It doesn't have to be that, it could be anything. But notice that at points of contact between different crystals or grains within that system, and there's melt against them both as well. If we think about what happens at high pressure and temperature, high temperature is what's really required, is that this box here, this big box, will convert to this, and this small blow up right here will convert to this. And the features that you see in equilibrium microstructure are what we sometimes refer to as sintered grains with a dry, that is fluid absent grain boundary between them, and a dihedral angle, that is the angle of these two curved surfaces where they come together at that point, as characterizing the geometry of the melt. So to a first approximation, that's true, and this angle theta, the dihedral angle, is characteristic of the particular system. In particular, it's determined by the relative values of the grain boundary energy and the crystal fluid interface energy of that interface right there. Okay, so I'll now talk about equilibrium microstructure in this way, but I will emphasize that this requires high temperature because to get from this box right here to this one here, you need dissolution, diffusion, and reprecipitation. You have to move constituents of the solid grains around in that system in order to create the equilibrium geometry. So it doesn't really require high pressure, but since in the Earth high pressure goes along with high temperature, usually we think in terms of both of those being required. Okay, what sort of geologic settings then might we imagine this equilibrium microstructure to develop? I've summarized several of them here. One would be where basalt segregation from the upper mantle occurs at mid-ocean ridges. This is an upwelling regime. In that case, the equilibrium microstructure would involve olivine and basaltic liquid, but there are many other environments involving other kinds of fluids, metamorphic dewatering in the mid to lower crust, for example, and upward flux of fluids. As long as the minerals are soluble in the fluid of interest, then there is a chance at least that these principles will govern the microstructure and therefore mass transport in the system. Migmatite evolution, partial melting in the lower crust is another possibility. And this one right here, one of my favorites, release of fluids from devolatilization reactions going on in subduction zones. So there are some settings to think about as we progress through the talk today. Now, there are two sort of M-member fluid topologies that you'll hear people talking about. These are highly simplified in these diagrams, but I think these will help you visualize in 2 and 3 dimensions what we're talking about. There is a case of interconnected fluid, and this applies I won't try to explain why just now, but for values of that dihedral angle of 60 degrees or less, this is the fluid topology that obtains. This is a 2-dimensional polished section through a sample with interconnected fluid, in this case it's aqueous fluid. This is a 3-dimensional representation of the same thing. I confess that that is not actually a picture of this. This is an SEM photograph of a pumice, but it has exactly the same kind of texture as the interconnected fluid in this picture here. So it's a useful thing to show the geometry of the fluid. Okay, the other case is when the when the fluid is present as non-interconnected pores or isolated pores. Here's a 2-dimensional section, and this is a transmitted light photomicrograph actually taken on a quartzite. You can see here where the crystal fluid boundaries come together, they form an angle less than 60 degrees. Here the triangular features are bloated, and that's telling us it's greater than 60 degrees. You can see these sort of bloated pores. Those sit at the corners of grains in that sample. So that gives you a pretty good visualization. Now, when we come comes to discussing mass transport, we really aren't very interested in this case right here. That isn't to say that there are not fluids that show this in the Earth, and indeed there are many, but in this case, there's no connectivity among the pores, and therefore no possibility for diffusive transport, significant diffusive transport or flow. You could think of the fluid in this case as playing a role both in our understanding of the Earth and in the behavior of this system, similar to fluid inclusions within minerals. Whereas in this case, they provide, the fluid here provides sort of a racetrack for diffusion through that sample and also for porous flow. Okay, just in case you haven't been keeping up on the literature over the last 10 years or so, I think one of the useful thing that I can do is just to show a connectivity summary. Here are several different kinds of fluids and melts, and indicated next to each one is the answer to the question, is the fluid interconnected? For aqueous fluids, the answer is that they are sometimes interconnected. The details depend on the mineral, identity of the mineral, pressure, temperature, and X being sort of composition of the fluid, solute composition. CO2-rich fluids, on the other hand, are never interconnected, at least in over the range of systems that have been studied so far. Carbonate melts, which would be relevant maybe to the upper mantle, are always interconnected, even down to diminishingly small amounts of melt in the system. Silicate melts generally are interconnected, but they, in crustal melting situations, they may form isolated pores at low melt fraction. Lastly is metal oxysulfide melts, which might be relevant, say, to formation of the Earth's core. These are sometimes interconnected, and whether or not they are depends on the oxygen content of the system. Not of the system, but of the metal oxysulfide melt. Okay, so there's a summary. Those are not all our own results. So forgive me for not giving credit, but it's just for a lack of time. So that's an overview of how we think about the mass transport involving fluids in the Earth today. And I'd like to move on now to talk about some recent results from our laboratory. And these are 3 different projects. These first 2 have actually been published, but I think maybe from the nature of the audience today, you probably haven't read these papers in detail, so it's worth my talking about them. And so first I'm going to very briefly tell you about diffusion in supercritical fluids as a mass transport mechanism. I'll then move on to talk about permeability. Now, the connection, I hope you can see the connection back to the figures that I've just shown about showing the interconnected porosity. In order for diffusion through a fluid to be effective, that fluid must be interconnected. In order for the rock to have any permeability, that fluid must be interconnected. And the third subject that I'll talk about is something that I refer to as lithologic partitioning of fluids, which simply says that if you have 2 or more lithologic units, you could read rock types into that statement, that are juxtaposed, that the fluid will be concentrated within one of those relative to the others. This is something that I have talked about publicly, but we have not published anything yet on that subject. Okay, so I'll go through these one at a time without too much discussion of the experimental details. So here again is our picture of an interconnected fluid. Think about it this way. If you had, and we're now about to embark on a discussion of diffusion, if you have a source, this could also be a sink for some diffusant in a system where the fluid looks like this. The transport distance through that system depends on basically 3 things. One is the tortuosity of the diffusion path, which I've indicated with these wiggly dotted lines. Another is the interaction of the solute diffusant with the minerals. The mineral grains sit right here. If those interact with the diffusing solute, that will certainly affect the transport distance through it. And the last thing is the diffusivity of the solute in the fluid. If we're concerned, for example, about just how far a diffusing atom could get into this system, that is limited by the diffusivity of the solute in the fluid. A few years ago, I did some experiments on fluid-bearing and partially melted rocks that examined bulk diffusion. I measured bulk diffusivities through a material like this. And then I tried to relate that to the kinds of fluids that were present in the system and whether they were interconnected or not. And when the fluid was basaltic melt, so picture this as basaltic melt with among olivine grains, I was able to model the process numerically quite well. But one of the reasons I could do that is that diffusivity information was available for the melt. In other words, I didn't have to make any guesses about how fast things could diffuse when unimpeded by interaction with a solid, how fast things could diffuse through the melt. But when faced with modeling it for the case of a fluid filling these interconnected pores, I was at a loss because there was no diffusivity information for fluids. So what I'll tell you about now is our recent results on diffusion through a system like this when the fluid is aqueous fluid at pretty extreme conditions of up to 900 degrees or so and 10 kilobars. Here's a little bit, a conceptual model that maybe makes this a little bit easier to appreciate if you haven't thought about it before. Here again is our diffusant source or sink. Here's our rock as just a model rock with everything straightened out, no tortuosity to it. It has grain boundaries right here. It has fluid-filled channels right here. What I'd like you to come away with from this figure is that what limits the transport distance through this material is how fast atoms can race down these fluid-filled channels, because those are definitely the high diffusivity pathways in the system. So we set out to determine the diffusivity for fluids because we already had information on melts that we could use in modeling this kind of process. This was a tricky thing to do, and this project I undertook with Dave Work, and as I said, it was Dave's perseverance and resourcefulness that really put this idea, made this idea a reality. What we sought to measure was silica diffusion. It's a very important solute in aqueous fluids at high pressures and temperatures, and the most important component in some respects in the crust and upper mantle. The way we set out to measure this was to design a container, a double-chambered container, with one chamber down here that's cold, one that's up here that's hot. And I use those in a relative sense. You can see right here that we're not really implying a very big, over here, a very big temperature difference. This is about 800, this is about 750. But in both chambers are silica saturated. There are quartz grains here and quartz grains here. But what will happen is that these quartz grains will dissolve and material is transported down this capillary connecting the two chambers, and quartz will precipitate here. And what we had figured out ahead of time through numerical simulations was that if you simply allow this to reach steady state, which happens very quickly, you can simply solve Fick's first law. If you know the amount of material transported, this M for total mass of silica, you know the cross-sectional area of this capillary, you know time, you know the difference in concentration from the different solubilities, and the length of the capillary, then you can simply solve for the diffusivity. So this looks, in principle, really nice. It is difficult to implement. This is, for the experimentalists in the audience, this is the diffusion cell that we designed to actually do this. But I don't want to dwell on the details of that for now. This sort of conceptual drawing works pretty well. So, what were the results that came out of this study? We looked at diffusion over a very broad range of temperature, and indeed this isn't usually possible in studying diffusion in geologic materials. But because of the nature of the material we were working with, it was possible to cover a range from about 500 to 900 degrees C. These are the data. I'm not going to dwell on the significance of all these different points. This one right here is not ours. This is a previous estimate based on a rate of metamorphic reaction This is a Arrhenius type fit to the data. Now, what's really interesting about this Arrhenius equation, or the actual values of the diffusivity, is that here is heat conduction in rocks. It's about 10 to the minus 6 meters squared per second. That is thermal diffusion in rocks. Diffusion of atoms, of matter, has been regarded usually as not very effective over long distances, and one of the main reasons is that the thermal pulse or temperature increase needed to drive diffusion doesn't last long enough for diffusion to be effective, because in most systems, this Arrhenius line for diffusion of the components of interest is way, way down here, many orders of magnitude below heat conduction. So what's interesting about these results is that these are the first diffusivities that really are almost bumping up against heat conduction in rocks. Well, within an order of magnitude or so at, say, 7 to 900 degrees. So you can move things pretty far by diffusion in supercritical fluid at these conditions. Here's a very simple model showing that. These are maximum transport distances in the sense that you assume no interaction with the host solids and just solve this simple approximation of the characteristic diffusive transport distance. And you see that in a million, here's the diffusion distance right here, and here's time in millions of years. So you see that if you're at a mid to lower crustal temperature of 600 degrees, you're talking about characteristic diffusion distances pushing a kilometer. And that really had not been taken very seriously as a possibility for diffusive transport in the past. But our numbers really show that under the right circumstances, diffusion really can be quite effective when there is a fluid phase present. Okay. That means also that any process that is controlled by diffusion, and one such process is infiltration of a fluid into a previously dry rock. So this is an initially fluid-free rock right here. I've drawn it to have a nice equilibrium microstructure. Here's a fluid source, and you probably won't really want to think about this as a reservoir of fluid. Maybe it's a devolatilization reaction going in this region right here. But the idea is that if this is previously fluid absent, the penetration of fluid into that rock is going to be, or the penetration rate will be determined by diffusion in the fluid, because what happens is the fluid dissolves its way along the grain edges, as shown right here, and the solute, if this were silica, quartz for example, the solute diffuses back out and deposits crystals out in this region right here. So the rate of this reaction, this process, would then be controlled or limited by the rate of silica diffusion outward from toward the source of the fluid. Now, if any of you went to the Melt Migration Symposium this afternoon and saw Mitch Nakamura's poster, he gave results for this kind of process that we recently produced in our lab, and you see some rates here. For the penetration rate for water into quartzite is about 3 millimeters per day. Doesn't sound like very much, but that is about a meter per year. So in a geological context, that could mean relatively large distances. That's at 820 degrees, drop down to 620, and you're about an order of magnitude slower. Okay, so, and incidentally, this process seems to have an activation energy about the same as the activation energy for diffusion of silica. So for this and other reasons, we're quite sure about the mechanism that is operating to allow the infiltration. Okay. I promised next there's some results on diffusion, and the lesson or conclusion is certainly that diffusion in fluids is fast, possibly geologically significant under some circumstances. The next thing I'd like to turn to is the permeability. Let's forget about trying to move things by diffusion and just ask the question, how fast can the fluid flow through a rock medium containing interconnected fluid? Okay, so here's a sort of conceptual diagram right here. Here's our interconnected fluid geometry. Here we're supposing instead of a source of diffusion that we have high fluid pressure here, relatively low fluid pressure here, and we're asking the question, how fast will the fluid migrate through that network of channelways? This would be governed, of course, by Darcy's law. This is the simplest statement of Darcy's law right here. Fluid flow velocity depends on the fluid pressure gradient, the difference from here to here, the fluid viscosity, mu right here, and the rock permeability. And this right here, is what has really been up for grabs over the last 20 years, maybe really 10 years since people began to publish data on it. The estimates in permeability for systems like this ranged over somewhere between 4 and 6 orders of magnitude, so really not enough to do much modeling with. So we set out to try to characterize the permeability of this kind of material. Okay, other researchers, Jim Taberzi and Jeff Roberts in particular, have been working on measuring permeability by electrical conductivity measurements. In other words, they measure the electrical conductivity, estimate permeability from that. Uli Faul, another intellectual descendant of Harvey Waff, has been working on characterizing the geometry of quench samples and estimating permeability from theory. Well, we decided we were going to be really direct. We were going to actually measure the permeability on samples synthesized at high pressure and temperature. We just put a lot of mineral powder in a thick-walled can or container like this with fluid, hold it at high pressure and temperature for a long time till we've achieved an equilibrium microstructure, cut the thing open at the ends. Here you see it cut open, and then just measure how fast we can pass a gas through that sample. From that, you can extract permeability. So this, in a way, is a material-independent property because it doesn't really matter what the mineral is. What matters is that we've achieved a geometry that is an equilibrium microstructure. And the permeability then should be fairly generally representative of other materials that qualify in that respect. So here are our measured permeabilities. These came out very late last year in an EPSL paper. This looks like so we did some experiments that proved that the theory was right. Here is Van Bargen and Wass theoretically estimated permeability in the dashed gray line, and this is a fit to our data right here, and the agreement looks remarkably good. In fact, we were very surprised about that because we expected some differences because of the simplifying assumptions they had to make in order to calculate permeabilities. But I should say the other estimates range from a couple of orders of magnitude up here to another 2 to 4 orders of magnitude down here. So I'm showing only the theoretical curve that our experimental data do ultimately agree with. And this is the relationship that we found to fit. D is the grain diameter, phi is the fluid fraction, and this is a constant which we've set at 200, or that is the result of the fit to these data. Now these are for quartzites with water in them, but as I said, as long as the system you're interested in has a microstructural resemblance to quartzite plus water, then the same permeability should apply. Now it turns out that that probably is rarely true. I'm going to give a couple reasons for that toward the end of my talk today, and Dave Wark is going to discuss it in some detail at his talk tomorrow in the Melt Migration Symposium. Okay, maybe I'll keep that up for a couple of minutes just to note that the limitations to this data are, first of all, this is a monomineralic sample, and I'd ask even of the geophysicists in the audience, is that a realistic rock? And the answer is certainly no. So these data have to be taken with a grain of salt in that respect. These represent a highly simplified system. These also show a you might think of it as a classical wetting structure. In other words, the interconnected porosity really does look very much like that pumice that I keep showing pictures of. And we now know that that is not necessarily true for many materials. But I think if you can grant those limitations, that this is a generally valid fit to or relationship for permeability of rocks exhibiting equilibrium microstructure. Okay, and the third sort of sub-project or aspect that I'd like to talk about today before winding things up is the fact that we now believe fluids are lithologically partitioned. And I did introduce that phrase at the outset and said what we mean by this is simply that if you have two different rock types that are juxtaposed and fluid in that system, that the fluid will show a preference for one of those rock types relative to another. Theoretically, you can show that this has to be true, but no one had really validated that experimentally. So this is another aspect that we've been working on. I'll show how it bears on mass transport in a few minutes. Let's just to explain in a very broad brush way the reason that we expect this phenomenon to occur. Comes back to this equilibrium wetting geometry. Here is a dry grain edge. In other words, there's a grain right here, one right here, one right here. Three grains coming together. These are grain boundaries between them, right here, and this is what we refer to as a triple junction. You can show for a given ratio of grain boundary energy to solid fluid interfacial energy, is energy of this boundary right here, that when you introduce fluid along that boundary, you lower the interfacial energy of the system. So a system should tend to, you could think of it as pulling in a fluid along those grain edges in order to reduce the interfacial energy. So for cases where the fluid is interconnected, if we plucked out a single grain, the topology of the fluid would look something like this. And that system would have a lower total interfacial energy. So one way to think about it is in terms of a simple graph, which I show at the bottom of the page. This is total interfacial energy in the system versus percent fluid. As you begin to add fluid, initially at least for wetting, edge wetting fluids, the total interfacial energy will drop. It will bottom out and then come back up again. We refer to this minimum as the minimum energy fluid fraction. And all that says is that there is some fluid fraction that represents, relative to neighboring fluid fractions, a minimum interfacial energy in the system. But what I'd ask you to realize is that this minimum applies to one particular rock type. And if you have two rock types of differing mineralogy in communication with one another, the fluid must show a preference for one relative to the other. I was going to show some, maybe I will show this diagram. These are actual model calculations for, remember what the value, what theta is. It's this angle right here. For different values of theta, which the decrease in total system interfacial energy follows curves like this. So this is fluid fraction phi across the bottom, total system interfacial energy. And as long as theta is below about, what would it be, about 80 degrees or so, there is an initial drop in total system interfacial energy, bottoming out, and then a rise like this. So these are for an idealized model, but we can be pretty sure that the same kind of behavior, if not quantitatively identical to this, would happen with any rock type. Okay, so the point is then, if we were to take two different rocks shown schematically right here, rock A and rock B, these have different curves of the type that I just showed for total interfacial energy. And if you began to introduce water or fluid of any kind into this system, there would be a preference for rock B. That might be manifest by migration of fluid from rock A to rock B if this were, for example, a source of fluid. The main point is that there is a minimum interfacial energy configuration that will not mean equal distribution of fluid between the two rock types. Okay, so that in a very simple way is the theory. Let's see if you can actually prove it by experiments. The answer is yes, you can prove it very nicely for some very simple analog materials. I had the most success with quartz and fluorite and quartz and calcite. Not really good terrestrial materials in a bulk sense, but very nice for showing this behavior because both of these materials achieve an equilibrium microstructure very readily in the laboratory. And so we thought it would be relatively easy for these to show this effect of lithologic partitioning. So here is, you could think of this as a partitioning couple. Here's quartzite here, and this is a fluorite rock, calcium fluoride. In simple terms, you simply introduce water to this at the start, let it sit there for a while, and then measure the porosity afterward. And I think you can see here's a blow up of this region right here in the fluorite. There's very little fluid present here, and these are the measured fluid amounts that come from image processing or image analysis. And here's a blow up of this region right here in the quartzite. And it's obvious, I think, that the porosity here is much greater than it is here. So there's been you could even think of it as a sort of a sucking effect of fluid out of the fluorite into the quartzite. Okay, we have managed to show that this works with other materials, a little more realistic than fluorite and quartz. This is a very similar example for clinopyroxene in quartz. Here are the conditions right here. This is quartzite here. This is iron-rich clinopyroxenite right here. And you see some blow-ups of, this one is that frame right there. So relatively high magnification right here. You can see the porosity. I think you can deduce that the porosity is quite a lot smaller here. These bright blebs are silver. The container hosting these materials is silver, and sometimes it gets into the deep into the materials. In any case, the porosity is quite a bit greater here by a factor of somewhere between 2 and 3, or maybe 3 and 4 in that case. Now, I should say that in this particular case, because there's quite a significant difference in grain size, the quartzite is considerably coarser grained than the clinopyroxenite. It is possible what we're seeing here is a grain size effect, not a compositional effect. Because we will show, in fact, Dave Work will talk a little bit about this tomorrow, that fluid should be partitioned, given a given composition of rock in a mineralogical sense, fluids will be partitioned into the finer grain of the two rocks. Okay, so we're not completely sure that that's not what we're seeing right here, but it does at least demonstrate for some geologically plausible materials that this lithologic partitioning is a fact of life. Now, why might that be important to mass transport in the Earth? I think I can show that with this cartoon. Possible consequences of lithologic partitioning. The idea is simply that if you have this looks like a schematic for a metamorphic terrain of some kind. If you have a unit that draws in fluid due to this partitioning effect, that unit may become what John Ferry has referred to as a metamorphic aquifer. In other words, it increases its porosity and permeability by drawing fluid from the surrounding material, and thus enabling rapid transport through that material relative to the other layers. Okay, so we think these things go on in the Earth. Unfortunately, we don't have a lot of data for a wide variety of materials, but there are some other groups working on this. In particular, my former student, Bill Menarick, and James Bernan are working on some mantle analog systems. Okay. So you've just seen sort of 3 different aspects of on this topic of mass transport in the Earth, sort of fluid-assisted mass transport. I think you've gotten a flavor of the kinds of things that we're working on. But what I'd like to do now is turn to some areas where we don't have actual results, but where maybe the next AGU or GSA meeting will be able to present some results, just to give you a glimpse of things to come and some of the problem areas that we see. So I'll call this sort of work in progress. And there are basically 3 things that I want to talk about. One is effects of the following on microstructure and permeability. One is faceting. I hinted at this a little bit early on in the talk, and I want to come back to that. Another aspect is fluid localization. And a final aspect is the role of any accessory phases, what role they might play in permeability of the system. So let's just quickly go through these just to show you really that in spite of all the, I hope, good stuff that I just showed, we really still don't know very much yet. One thing we don't know much about is the effect of faceting of grains on, say, on transport properties, in particular on permeability. Now this is a blow-up of the picture, the image from Lithologic that I showed very early on. These are olivine grains and this is basaltic melt. And if you've been on your toes, visually speaking, you'll note that there are some features in there that don't look like the smoothly curved crystal fluid boundaries that I have implied exist under microstructural equilibrium. And indeed, you see a lot of very straight lines bounding these melt pools. Those are actual facets on the grains of olivine. And those are the lowest energy, surface energy configuration, at least locally, and they change the geometry of the melt a great deal. The topology of this melt probably doesn't look in 3 dimensions very much like the images that I've been showing previously. Lithologic believes that melt is segregated into these pools to some extent, that sort of dries off the triple junctions where these little triangles are, thereby dramatically reducing permeability. And his permeability estimates, incidentally, for rock like this are orders of magnitude below the ones that we've actually measured for quartzite. So there definitely has to be something, there's something to sort out there. We can't actually measure permeability on this particular system because we rely on creating porosity, real porosity with a fluid phase that we can then push air through after the synthesis experiment to measure the permeability. You can't do that with these samples. Here's amphibole plus water. Now this has a pretty large fluid fraction, unrealistically large, but notice these are crystals that grew during the course of the synthesis experiment. And the texture of that or microstructure of that bears very little resemblance to the things that I've shown. The microstructure is determined by and large by the shapes of those olivine grains. So the dihedral angle, the dominance of the dihedral angle in determining melt topology is probably completely missing in this system. So this is open for, or up for grabs. We're going to try to measure permeabilities of samples that look like this to try to get another end member behavior. Okay, the second thing I wanted to mention in connection with permeability measurements is something that I'm calling fluid localization. We worked with, to get our measured permeabilities, monomineralic rocks, rock analogs, pure quartz and also pure calcite. Again, they're nice materials to work with, but they are probably, there's only so far you can take them as analogs of earth materials. These are samples of fluorite with what started out as little knots of silica glass added to them. What I wanted to produce here was a sample with large grains and very small grains of a different phase. What happens in this case, here's the the light gray material is fluorite, the darker gray material is quartz. Quartz crystals formed by crystallization of the silica glass, and you see the black areas are porosity, what is fluid filled. But what happens in this instance, and we're not completely sure whether it's a chemical effect or a grain size effect, is that the fluid in the system gets drawn into these fine-grained knots. And if you imagine the bulk permeability of the material, if you are sucking fluid into these small fine-grained knots, that is going to and if those knots are not interconnected, you will dramatically decrease the permeability of the system. So here we're moving toward maybe a more realistic texture for some kinds of metamorphic rocks, and what we're concluding is that our measured permeabilities for the simple system are probably not going to apply to this case right here. So fluid localization, we call it, is another, just a little bit different scale of fluid partitioning as I discussed it a few minutes ago. Okay, and lastly, the last sort of um, new research front in this area that we're working on. Oh, sorry, that's not the one. Well, I can't find my summary, so I'll just go right to it. Is what about a role played by what we'll call accessory minerals? And I really mean that sort of here in a microstructural or textural sense, an accessory mineral being something that has a very small grain size relative to the rest of the grains in the system. This is olivine plus basalt. It's a very nice image. You can see the olivine grains very clearly. You can see some dry grain boundaries here through here like that. And this is melt right here, quench basaltic melt. The very bright rims on the olivine are quench growth material precipitated during quench. But there is something else here that took us a while to puzzle out, actually, and those are these dark or black features right here. Those are not pores. Some of you are probably recognizing right away, since this is a backscattered electron image, that those are very low density or low mean Z material. Turns out that's graphite. This sample was synthesized in graphite container, and there's enough solubility in the melt that you get precipitated graphite through this system. Now, in a former life, I thought a lot about accessory minerals in the mantle from a geochemical standpoint. And when I began working on permeability, it never occurred to me that those could play a role in determining permeability, simply because most or all accessory minerals that I can imagine for any significant degree of melting are gone. They're part of the melt. They simply are too soluble in the melt to persist during melting. But this is graphite, and what it's telling us is that if this system has enough graphite in it, I think we calculated something like 400 ppm is necessary to form this texture right here. That is going to remarkably or markedly change the permeability of this system. These are little plates. Many of them are oriented at high angles to the channels through which we're trying to get flow. And so it may be that we really don't know as much as we thought about permeability of the mantle if a small minor phase like graphite can change the permeability that way. We're trying to reproduce these textures on samples in which we can actually measure permeabilities, but it doesn't take too much imagination to state that these are going to reduce the permeability remarkably. Okay, so there's still a lot of work to do. We don't know all the governing parameters to fluid and melt transport in the Earth. In connection with the graphite story, I will throw up this diagram. This is taken from Steve Haggerty about 9 years ago now. Don't pay any attention to the rest of Steve's stuff here. The only thing I really wanted to call attention to was the graphite to diamond transition. If you accept that there's a bit of carbon in the mantle and recognize the possible effect on permeability, this could be a permeability boundary right here, because graphite will have according to the textures we just looked at, a significant effect on permeability. Diamond, because of its higher density and different habit, is not likely to. So this graphite to diamond transition could be a permeability boundary. As long as I'm really sticking my neck out and waving my arms sort of frantically, I might add too that these little crystals of graphite could as well be bubbles. If those were CO2 bubbles, they would have the same effect on permeability if they're located in the right places in that system. In other words, you could dramatically drop the permeability by sort of vapor phase clogging of the system. Okay, well, I'm going to stop right there because I think my time is just about out. I wanted to show one other slide. This is mostly a PR plug for the Melt Migration Symposium. I was feeling guilty after working up all my transparencies about the fact that I hadn't talked very much about other people's work, and I wanted to call attention. This is stuff that's going on at RPI that I've just talked about. These are other research groups who really deserve a lot of credit. Many of them, you'll notice, are former students or colleagues of Harvey Woff, who started off this whole business about 20 years ago. Uli Fall, Jim Taberzi are two of them. So these are other people working on this problem as well. We don't own it by any means, and there's a lot of progress being made, in particular on rheology and deformation microstructure. Dave Kolstad and Greg Hirth have talks about those subjects at the Melt Migration Symposium. So thank you very much for your attention. I'll certainly answer any questions you might have.